Coming to the precipitation strengthening. So in the case of precipitation strengthening, a sloping solvent is required, and the treatment that is initially given is solutionizing, where all the solute goes into the solid solution. Then at higher temperatures, all the solute goes into the solid solution, and upon quenching and aging at lower temperature, the excess solute comes out in the form of precipitates. So this is precipitation hardening. And we consider example of aluminum copper alloy. So what are the phases that occur? What are the transition phases that occur during aging? So solutionizing, then quenching. Quenching is mainly to retain the supersaturated solid solution, and aging at lower temperature so that excess solute comes out in the form of precipitates. So in the case of aluminum copper alloy system, initially with respect to the aging time, initially GP1 zones form. Next is GP2 zone. This is also known as theta double prime. Then comes theta prime, then finally the precipitate undergoes coarsening and forms theta phase, equilibrium phase, CuAl2. And this is a plot between the hardness due to the various transition phases that occur during the aging of an aluminum copper alloy with respect to aging time. So peak hardness is achieved by the formation of theta prime, and still with increase in aging time, theta, the equilibrium phase CuAl2 forms from theta prime, from the transition phase theta prime. From here the coherency is lost. The lattice matching is lost, the coherency is lost. So this is the region underaged, and this is overaged, underaged and overaged. So how this fine precipitate particles act as hindrance to the dislocation motion? They themselves, these precipitate particles, they act obstacles to the dislocation motion. So before going into this figure, a small figure I need to explain is about the hindrance to the dislocation motion by the obstacles, which are very fine, and the spacing between the obstacles is less. And in the case of random obstacles, randomly oriented obstacles, where the spacing between the obstacles is large. So in this figure we consider precipitates are obstacles to the moving dislocation. A dislocation moving in this direction, it is hindered by the obstacles. So for the dislocation to bypass, to overcome or to break away from these obstacles, it requires higher stress. So the stress that is required for the dislocation to break away from these obstacles, it depends upon the spacing between the obstacles, L, the spacing between the obstacles, and the angle. This is the angle for the dislocation to bend at the obstacles. The amount of angle the dislocation bends at the obstacle. If the spacing is very, very large, simply the dislocations can easily move. For the case where the spacing is very, very large, and if the angle is also large, if the angle is 180 degrees, then the stress required for the dislocation to overcome these obstacles or to break away from these obstacles is very easy. So in this case, the distance between the obstacles or spacing between the obstacles is very small, and the dislocation has to bend to overcome these obstacles. So to bend at the dislocation, the angle is given phi. So smaller the angle, more stress is required for the dislocation to break away from the obstacles. Smaller the spacing, more stress for the dislocation to break away from the obstacles. If the spacing is large, or if the angle is large, if it approaches 180 degrees, almost the dislocation need not bend. Okay. So the obstacles, that is the second phase particles, whether it is dispersoids or the precipitates, if they are fine and more in number, then it creates more obstacles, it creates more hindrance for the dislocation to pass. And in the case of precipitation hardening system or the precipitation hardening alloys, the one example is the aluminum copper, which is discussed now, is aluminum copper alloy. So initially, after solutionizing, to take into the solute element, all the solute into solid solution, and then quenching to retain the supersaturated solution, and then aging at lower temperatures so as to precipitate the excess solute from the matrix. So in the initial stage with respect to the aging time, small clusters are formed. Clusters means group of atoms together is known as cluster. Small cluster of the solute atoms, copper clusters, they form. So thereby they create strains, lattice strains, and the hardening increase, or the strength of the material increase, hardness increase when compared to the solid solution. Formation of small clusters creates some hardness, increase in hardness when compared to the completely solutionized alloy, that is a solid solution alloy. Because of the formation of the cluster, it creates some lattice strains. With further aging, theta double prime, that is also known as GP2 zones, form. Further larger clusters form. These clusters grow in size to larger lumps, thereby more strains are created. So these clusters, they are named after the scientist Giner Preston, who has first observed these clusters by means of X-ray diffraction techniques. Thereby these copper clusters, they are known as GP zone, Giner Preston zones. So this is known as GP zone. These copper clusters, they are first identified by the scientists by means of X-ray diffraction techniques, Giner and Preston. So these are known as GP zones. Initially aging, GP1 zones formed, which are small cluster of the solute atoms, which contribute to strengthening because of the lattice strains. With still further increase in aging time, these copper clusters grow in size and form theta double prime, where the strength or the hardness further increase because of the formation of this theta double prime, also known as GP2 zones, because of more lattice strains that are created. Then further increase in aging time, theta prime phase forms. COL to theta prime phase forms. So which increases the strength of the alloy, mainly due to the coherency between the lattice parameter of the precipitate and that of the matrix. Because of the lattice matching, coherency between the precipitate particles and that of the matrix, the hardness or the strength of the alloy still increases further. With further increase in aging time, the precipitate grows in size, that is, it coarsens to lower the interfacial energy. It undergoes coarsening by solid state diffusion, and it increases in size. And the coherency is lost, thereby the hardness comes down, and the formation of an equilibrium phase, theta phase forms, that is CuAl2 phase is formed. So these are the steps that are observed in the case of, or these are the various transition phases that are observed in the case of aluminum copper alloy, whereas generally this is the same is not followed in the case of other precipitation hardenable alloys. We have the formation of a coherent precipitate at slightly with increase in aging time, and then with still further increase in aging time, the coherency of the precipitate is lost. This is generally found in other precipitation hardenable alloys, but GP1, GP2 zones, these are generally found in the case of aluminum copper alloy systems, whereas in all other precipitation hardenable alloy systems we have the formation of a coherent precipitate where the strength increases, and with increase in aging time the coherency is lost and the precipitate undergoes coarsening and the hardness comes down, decreases. This is what is generally found in most of the precipitation hardenable alloy system. So GP1, GP2 zones, these are named after the scientist Guiner and Preston. These zones, they are the fine copper clusters of copper atoms, solute atoms, which form because of the strains created by the form, because of the strains that are generated due to these clusters, they cause hindrance to the dislocation motion. With still further increase in aging time, these clusters grow in size and forms theta prime, which is coherent with the matrix. Thereby the hardness increases, that is the peak hardness, and finally the coherency is lost with further increase in time, and the formation of equilibrium phase, theta phase, forms. Coarsening of the precipitates take place. Now what are the mechanisms by which a dislocation, a moving dislocation, the obstacles are the precipitate particles. Now what is the mechanism by which the dislocations has to move away or has to break through these precipitate particles to move? What mechanisms leads to strengthening? The two mechanisms that lead to strengthening of the precipitation hardenable alloys is dislocation cutting. Dislocation cutting, that is cutting mechanism by which the dislocation cuts the precipitate particles and then they move further. And second is the looping mechanism, which is given by Orawan, a scientist named Orawan looping. Orawan looping mechanism. So the two main strengthening mechanism in precipitation strengthening is, one is the cutting mechanism and second one is looping mechanism. These two mechanisms are based on how the dislocations break away through these obstacles, through these second phase particles. If the precipitate particles are very fine in size, smaller in size and soft, they can be easily cut by the dislocations. So the mechanism that operates when the precipitates are very fine is the cutting mechanism, and the mechanism that operates when the dislocations, they cannot cut the precipitate particles, when the precipitate particles are of larger in size, that is for the coarser precipitates, when the dislocation cannot cut through them, then the mechanism that operates is looping mechanism. That means the dislocation has to bend around the precipitate particles and it has to bypass them, because cutting is not possible. So cutting mechanism operates when the precipitates are very fine and soft, so the dislocation can easily cut the precipitate particles. And looping mechanism occurs when the precipitates are coarser. So the dislocation has to bend around the dislocation and then it has to bypass them. So both these mechanisms requires higher stress. The bending of the dislocation around the precipitate particles and cutting the precipitate particles. So when the precipitate particles are very fine, this is the precipitate particle or dislocation. This is an edge dislocation. If it has to move across the precipitate particles, so the obstacle to the edge dislocation is the precipitate. It has to overcome this obstacle. So it can overcome the obstacle when the precipitates are very fine. Cutting mechanism operates. So the edge dislocation, it cuts, it shears the precipitates. It shears the precipitate particle. So this is the passage of a dislocation through a precipitate which is fine in size. So the passage of the dislocation occurs by the cutting mechanism because these precipitates are shearable. They can be easily deformed or they can be easily cut by the moving dislocations. So which requires, it is not easy, it requires very high stress. So that is the strengthening mechanism. One is the cutting mechanism by which the edge dislocation, if it has to overcome the obstacle, it has to cut the precipitate particle, which requires high stress. Thereby the precipitate particle has been deformed, it has been sheared by the dislocation. When the precipitates are coarser in size, when they are not fine, when they are coarser and they cannot be cut by the dislocation, then the second mechanism that operates is looping mechanism. These are the two precipitates separated by the distance L. So for a dislocation to overcome this obstacle, it has to bend around the dislocation. It has to bend around the dislocation and then it has to bypass. So bending around the dislocation requires large amounts of stress. So this is the first one, is the cutting mechanism. When the precipitates are very fine, they are shearable by the dislocations. When the precipitates are coarser, the spacing between the dislocations, besides the stress required to bypass the dislocation, the dislocation has to bend around the dislocation. It has to form the loops around the precipitates. The dislocation has to bypass the obstacles, the precipitate particles, by forming loops around them. It has to bend around the precipitate particle, form loops, and then it has to bypass the obstacles, that is the precipitate particles. So these two are the main mechanisms in the case of precipitation hardening. Since the precipitates, if they are very fine in size, cutting mechanism operates, and if they are very coarser in size, the bending or bowing of the dislocation, that is Orawan looping, mechanism operates. So the one more plot which shows both cutting mechanism as well as looping mechanism with respect to the particle size. So this is with respect to the particle size R, particle size, and with respect to the strength or the stress required. So this is the cutting mechanism and this is the looping mechanism. Here you can see the curve is not a peak, a sharp peak. Moreover, it is blunt. Why? Because normally any precipitation hardenable alloy, it consists a mixture of both fine particles as well as coarse particles. So the contribution of this peak hardness or the maximum hardness or maximum strength is due to both the mechanisms, the cutting as well as the looping mechanism at the peak. So this is one plot which shows the stress required with respect to the particle size both the mechanisms, cutting mechanism and looping mechanism. So this is the stress required with respect to the particle size, the cutting mechanism that operates, and the looping mechanism. So the cutting mechanism operates when the particles are very, very fine in size, that is in the under-aged condition, and looping mechanism operates when the particles are coarser. So this is over-aged condition. So dispersion strengthening, it comes under the over-aged condition of the precipitation hardenable alloys. Okay, so this is about the precipitation strengthening and dispersion strengthening, where the strength is mainly due to the presence of the second phase particles, which are the obstacles to the dislocation motion. So the second phase particles are precipitates for the precipitation strengthening, and they are dispersoids for the case of dispersion strengthening. And the slight differences between, main differences between the precipitation hardening and dispersion hardening is also seen. Why all alloys are not precipitation hardenable? Because it requires some criteria for an alloy to be precipitation hardenable, that is the sloping solvents. And moreover, for the case of dispersion strengthening, theoretically infinite number of dispersion strengthened alloys can be fabricated. It can be made because it is simply mechanical alloying, mixing of metal matrix powders and inert oxide powders in a high energy ball mill, and then consolidation by compaction and consolidation by powder metallurgy techniques. And moreover, one more difference between the precipitation hardening alloys and the dispersion strengthening alloys is, in the case of precipitation strengthening alloys, the precipitate is coherent with that of the matrix, whereas there is no coherency between the dispersoid and that of the matrix. And among these two strengthening mechanism, precipitation hardening or precipitation strengthening, it has the highest strength when compared to all the strengthening mechanisms. But dispersion strengthening, it can retain its strength to even higher temperatures, where the precipitation strengthening comes down because the precipitates undergo coarsening at higher temperatures. So these are some of the differences. And moreover, in any of the precipitation hardening system, the main phases are formation of coherent precipitate phase, where the peak hardness is achieved, and then a coarse precipitate which is not coherent with that of the matrix phase forms at higher aging times or longer aging times. Whereas for the case of the aluminum copper alloy system, which we have seen various transition phases that may not be found for all the precipitation hardenable, but one thing it is found is, in all the precipitation hardenable alloy systems, is formation of coherent precipitate phase, and with still further increase in time, the coherency is lost and precipitate coarsening takes place. And the two mechanisms that operate are the cutting mechanism, where the dislocation cuts the precipitate particle when it is very, very fine, and the looping mechanism, when the precipitate is coarse, the dislocation bends around the dislocation to bypass it. And that looping mechanism is also known as Oravan looping mechanism. Next, one more diagram which shows the shear stress versus shear strain for the case of aluminum copper alloy system. For the case of pure metal, what is the strength? For the case of solid solution, what is the strength? And overaged condition, underaged condition, and peak-aged conditions. So shear stress versus shear strain diagram for the various stages of aluminum copper alloy system. So shear stress versus shear strain curve for various stages, shear stress versus shear strain curve for various stages of aluminum copper alloy system. So for the case of pure metal, which has some strength, for the case of pure metal, that is pure aluminum, Then for the case of solid solution, when the alloy is solutionized, all the solute goes into the solid solution, it has higher yield stress. Solid solution, it has higher yield stress than that of pure metal because of the lattice strings by the solute atoms. The next is the formation of the ZP zones, ZP1 and ZP2 zones. When the alloy is aged to form the ZP zones, increase in yield strength occurs and slightly a yield drop occurs, and low amount of strain hardening. This is for the case of ZP zones. Then when it is aged to peak hardness, then it is overaged. It is overaged. The various stages which are observed in the case of aluminum copper system, the stress strain curves for these various stages. So this is for the case of pure metal, which has some strength, and solid solution, the strength is higher than that of the pure metal. That is because of solid solution strengthening, because of the lattice strains of the solute atoms and that of the dislocation interaction. Then, but the rate of strain hardening is low. That is, the slope of the curve is low for the case of solid solution. Then once it is aged, aging starts, the initial phases that are formed, transition phases that are formed are ZP1 and ZP2 zones. So the yield stress increases significantly for this case, and slight drop occurs, yield drop occurs, and then again the rate of strain hardening is low, and again the rate of strain hardening is low. The reason why the yield strength increases is known because of the formation of very fine particles, fine precipitates. So for the dislocation, to overcome these obstacles, it has to cut the precipitates. It has to cut these fine particles, ZP1, ZP2 zones, which requires more stress. Thereby the yield stress increases significantly when compared to the solid solution because of the cutting mechanism. Cutting operates at such high stress. So once the cutting operates, there is a drop in the stress because the dislocations, they cut the obstacles, they cut these particles. So once the cutting process or the cutting operation starts, there is a slight drop in the yield stress and the rate of strain hardening is low. And when it is aged to peak hardness, the yield strength, it is slightly lower than that of the ZP zone because of the looping mechanism, but the rate of strain hardening is high. That is, the slope of the curve is high. The rate of strain hardening is higher for the looping mechanism when compared to the cutting mechanism. Cutting mechanism, it requires more stress. Thereby, there is an increase in yield stress when compared to the aged to the peak hardness. So once the cutting mechanism starts, so these particles, they are sheared by the dislocations, and the particles, the shearable precipitates, they become still finer and finer. Thereby the rate of strain hardening is lower. But for the case of looping mechanism, the yield stress is lower than for the ZP zones, that is when it is aged to peak hardness, but the rate of strain hardening is very high. Even though it shows a slight decrease in yield strength, but the rate of strain hardening is very high. And for the case of overaged, the yield strength is lower, but the rate of strain hardening is also higher. Why? Because the dislocations, tangling of the dislocations occurs, which increases the strain hardening or the rate of strain hardening. In the overaged, the yield strength is lower, but the dislocations which forms loops around the precipitate particles, the coarser precipitate particles, because of these loops that are formed, the dislocations, they form tangles, and the rate of strain hardening is higher because of the formation of these tangles. So this is the stress strain curve for the case of aluminum copper alloy system for various stages. So from this graph, the main point that is clear is cutting mechanism lowers the strain hardening. The yield strength is higher for the case of cutting mechanism, but the rate of strain hardening is lower. And for the case of looping mechanism, the yield strength is lower than for the cutting mechanism, but the rate of strain hardening is higher. So for the case of cutting mechanism, yield strength is higher, rate of strain hardening is lower. And for the case of looping mechanism, the yield strength is lower, but the rate of strain hardening is higher. So this is about the stress strain curves for the different phases of aluminum copper alloy system. And last but not the least is the fiber strengthening. So this fiber strengthening, it is for the case of composite materials, where fibers are incorporated, very fine fibers are incorporated into a soft ductile matrix. The matrix is continuous, it is soft and ductile, whereas these fibers, they are of very high strength and have very high modulus. So these are fibers, they are incorporated in the matrix mainly to increase the strength of that material. Very high strength and high strength to weight ratio is achieved for this type of materials. So these fibers, they carry essentially all the load, and the matrix transfers the load onto the fibers. The other function of the matrix is to see that moreover the fibers, they are inert with respect to that of the matrix. They don't react with the matrix. So the other function of the matrix, apart from transferring the load to the fibers, is to see that there is no surface damage that occurs to the fibers. So this matrix phase is completely surrounded, as well as it is continuous, so that the fibers do not get damaged. It also transmits the load to the fibers. And any cracks which occurs due to the breakage of the fibers, it makes the crack tip blunt, so that the crack cannot propagate easily. So this is about the fiber strengthening, where for the case of fibers, continuous fibers, according to the rule of mixtures, the property of the composite, whether it is a modulus or any property of the composite, it is given by the modulus of the matrix into the volume fraction of the matrix plus the modulus of the fibers and volume fraction of the fibers. E stands here for the modulus and subscript C stands for the composite. So modulus of the total composite, which has the two phases, the matrix phase and the reinforcement phase, that is the fiber phase, fine fiber phase, is equal to, this is the modulus of the matrix. F subscript M stands for the volume fraction of the matrix, plus E subscript F stands for modulus of the fiber, and F subscript F stands for volume fraction of the fiber. So this is about fiber strengthening. So this is about the strengthening mechanisms. So the next we move on to the material testing part, where the mechanical properties like hardness, tension, tensile strength, yield strength, modulus, ductility. So all these important properties. How to determine these properties? What are the tests that are conducted to determine these properties? And what are the metallurgical variables or the metallurgical factors that affect these properties? What is the effect of metallurgical variables on mechanical behavior of metals? That we are going to study in the next modules. So till now, the topics that I have covered. So any doubts you have in the topics that I have covered, please do contact me. And some information about the GATE aspirants, those who are looking forward to write the GATE exam. So what type of questions that generally appears in the GATE exam? How to prepare for the GATE exam? My suggestion is, if you learn the concept, if the concept is understood very clearly, the basic concepts are clear to you, then it is easy for you to answer any type of question, whether it is a descriptive type or a short answer type, or if you are asked to justify your answer, whether it is true or false, and justify your answer, or else to solve a problem. It is easy for you once the basic concepts are understood. So please go through the lectures, previous lectures, as well as the reading material that is given to you, and try to solve the previous GATE papers. So if you have not yet seen the GATE papers, some of the papers I have gone through right from 2007 onwards. 2007, 2008, 9, 10 and 11. So from these previous GATE papers, I have gone through for this course, for this mechanical metallurgy course. And till now, what topics I have covered, I have taken some of those questions that have appeared from these topics. So that I would like to discuss now, so that you will have some understanding about the concept as well as how to prepare for the GATE exam. It is not that difficult to get a good GATE score. Only thing is, you need to understand the basic concepts. So some of the questions that I like to read out from the topics till now that I have covered, the questions related to that in some of the GATE papers, so that you will gain some confidence that if you put some effort as well as some determination, then you can easily cross this hurdle. So the question that has appeared in 2007. So till now, the topics that I have covered, I just go through only those questions. So this is from 2007. Question number 63. A pure low angle tilt boundary may be equivalently represented as tilt boundaries, low angle boundaries, sub boundaries. This already discussed in the previous lecture. If the misorientation, it is greater than 10 to 15 degrees, it is high angle grain boundary. Then these low angle grain boundaries, they are an array of edge dislocations. So the options given here is a pure low angle tilt boundary may be equivalently represented by an array of jogs on an edge dislocation, that is A bit. B, a cross grid of screw dislocations. A cross grid of screw dislocation is called a twist boundary, but here it is given tilt boundary. So a dislocation pile up consisting of both edge and screw dislocation. This is option C. And option 4 is an array of edge dislocations perpendicular to the slip plane. Since this topic has already been covered, if you go through the lecture as well as the reading material, you will find the option D is the correct answer. That is a low angle tilt boundary. It is an array of edge dislocations. Whereas a twist boundary, this is a cross grid of screw dislocations. And question number 65, it is a match the following. Group 1, it is given Hall pitch effect. that is first one, Hall pitch effect. Second, Bostinger effect. And third is Cottrell atmosphere. So all these things are known to you, and this has already been taught. Hall pitch relation, Bostinger effect, and Cottrell atmosphere. The other side is solute dislocation interaction. Solute dislocation interaction. Dislocation multiplication is the second one given. Dislocation multiplication. Third is grain boundary strengthening. Fourth, barreling, which comes under compression. Barreling under compression. And fifth is mechanical hysteresis during plasticity. Mechanical hysteresis during plasticity. So these are the options given. So from this you can easily see, for the Hall pitch relation, it is related to grain boundary strengthening. Yield stress is inversely proportional to the grain diameter. So Hall pitch, it is matched with 3. Cottrell atmosphere, it is solute dislocation interaction. Interstitial solute atoms, they occupy the positions below the edge dislocation and they form Cottrell atmospheres. Bostinger effect, it is mechanical hysteresis during plasticity, because Bostinger effect, I have drawn the figure. When a material is loaded in one direction, if it is loaded in tension, yielding occurs. Beyond yielding, if you unload that material and again reload that material in the opposite direction, the yield stress is lowered. This lowering of yield stress when a material is loaded in one direction followed by another direction is Bostinger effect. So if this is positive axis stress, that is tensile stress, if you have loaded the material in tension and again reload that material in compression, so this is the negative, that means you are compressing the material. So you have compressed that material. The material has yielded at a lower stress when compared to the previous one. And again unload that material. Again unload that material and again reload it. It forms an hysteresis loop. Neglecting small hysteresis effects, it forms a complete loop. So Bostinger effect is related to mechanical hysteresis which occurs during plasticity. So these are the 2 questions which I have found from the year 2007 related to the topics till now I have discussed. Still about fracture, tensional tensile testing, it is there. Since I have not covered these topics, I am not discussing those questions. But once those topics are covered, I again go through these papers, previous papers, and the questions related to those topics that will be discussed at the end of those topics. Then from one more paper, that is from 2009. A property, question number 5, a property that cannot be obtained from a tensile test. 4 options given. Tensile test, briefly I have discussed. That more detail I will discuss in the coming lectures. But at least to some extent I have taught to you, so I expect you can answer this question. A property that cannot be obtained from a tension test is: A is Young's modulus, B yield strength, C ultimate tensile strength, and D is endurance limit. This is what you have not heard, endurance limit. This comes under the topic fatigue. So the property that cannot be obtained from a tensile test is the endurance limit. Question number 15. A defect that is bounded by 2 mirror planes is option A twin, B stacking fault, C grain boundary, and D edge dislocation. So we have discussed about twinning. So twin plane, a twin boundary. So it forms a mirror image on other side of the twin boundary. The atoms within the twinned portion, they form a mirror image with the untwinned portion, and the boundary separating them is the twin boundary. So the answer for this is the twin. And one more, question, that is question number 34. Stacking fault energy plays an important role in determining the work hardening ability of a metal. In this context, the correct logical sequence is A. Stacking fault energy, easy cross slip and low work hardening. High stacking fault energy, it is easy to cross slip, low work hardening. This is the first option given. Second option is high stacking fault energy, difficult to cross slip and high work hardening. Third option is low stacking fault energy, easy to cross slip, low work hardening. And option D is low stacking fault energy, difficult to cross slip and low work hardening. So just in the today's lecture, we have discussed about the stacking fault energy. Stacking fault energy is low, wider is the faulted region and difficult to cross slip. If it is difficult to cross slip, higher is the strain hardening. Thereby, the answer for this is A. High stacking fault energy, it is easy to cross slip and work hardening is low. Question number 42. In today's class, I have explained about this precipitation hardenable alloy. During low temperature plastic deformation of an under-aged precipitation hardened alloy, dislocations, A option, climb to completely avoid the precipitate, loop around the precipitate, cross slip to completely avoid the precipitate, cut through the precipitate. When the precipitates are very fine, the dislocation cutting mechanism operates. So the option is D. So this is from the paper 2008. The first question, the yield point phenomena observed in annealed low carbon steels is due to the presence of, this is already known to you, that is due to the presence of interstitial elements, carbon and nitrogen. The options given are A. Silicon, B. Chromium, C. Phosphorus and D. Carbon. The option is D. In a tensile test of a ductile material necking start set, this has been discussed. Option is A. Lower yield stress, B. Upper yield stress, C. Ultimate tensile strength, D. Just before fracture. So the option is C. At the point of ultimate tensile strength, necking starts. And one problem is given to you. Question number 21. Please try out this problem. This problem is based on Hall-Pitch relation. A metal with an average grain size of 36 micrometers has an yield strength of 250 MPa, and that with 4 micrometers has 500 MPa. A metal which is having 36 grain size of 36 micrometer, it has yield strength sigma naught is equal to, that is sigma y, yield strength is equal to 250 MPa, and that with 4 micron meters, it has an yield strength of about 500 MPa. So what is the friction stress of the metal in MPa? Four options given, 31.2, 62.5, 125 and last option is 250. So the formula for this is yield stress is equal to friction stress plus K d to the power of minus half. Yield stress is given, grain diameter is given, K is the locking parameter, that is the constant for a material. You have to find out sigma I. So substitute these two. For the case of, find out sigma I from the equations. You have two equations, substitute for K and then find out sigma I. The answer comes to be 250 MPa. So these are the questions in the previous papers right from 2007 to 11 that I have found out. And one more is with respect to dispersion strengthening that I have discussed in today's class. Identify the attributes associated with dispersion hardened alloys. First option is dispersoids do not dissolve in the matrix even at higher temperature. Second is dispersoids are coherent with the matrix. That is wrong. Third is dispersoids impart creep resistance to the alloy. That is correct. And fourth is dispersoids improve the corrosion resistance of the alloy. So the attributes are the first and third option. So these are the few questions that I have found with related to the topics discussed till now from the previous GATE question papers right from 2007 to 2011. So my suggestion is please go through the lectures as well as to the reading material, understand the basic concepts, and if you have any doubts and for further clarifications, please do contact me.